Wilcoxon its various forms of mutation. It's the bread and butter, baby, what's your jam?
Buen dia, Bio 6611. In this lecture, we'll be talking about nonparametric methods more generally for hypothesis testing that we can use, primarily with R. We'll introduce the idea of the Wilcoxon rank sum test, introduce as well its asymptotic and exact derivations before walking through how we can do it in R. We will then see an example of the Wilcoxon signed rank test before looking at the sign test and a few implementations and examples we can do with that. Let's start by talking about the Wilcoxon rank sum test. The Wilcoxon rank sum test, also known as the Mann-Whitney U-test or the Wilcoxon Mann-Whitney test, so many names, is for two independent samples of quantitative data. The nonparametric two-sample test here is analogous to the parametric independent samples t-test, but it has nothing to do with comparing means, or even medians or distributions more generally. The Wilcoxon rank sum test is ultimately a comparison of the mean ranks between two different groups. Specifically speaking, the null hypothesis H0 is that the mean ranks are equal between the two groups. What we're going to derive in the following slides is the Wilcoxon rank sum approach, but we can note if you're familiar with or see information on the Mann-Whitney U-test, it has a different approach to computation, but ultimately is completely equivalent to the Wilcoxon rank sum test we will be discussing. First, some assumptions for the Wilcoxon rank sum test. One is that we have independent observations, and for example, we may achieve this by random sampling. We can also note the test is based on the probability an observation in sample 1 is greater than an observation in sample 2, or the ranking of those two samples. In other words, we can state the null hypothesis as the probability x1 is greater than x2 or equal to x2, which is equal to 0.5, so a 50-50 chance of being in either group, versus some different chance. Because this is a nonparametric test, it does not require normality, even for small n. We'll see we have example calculations for that are exact. For large enough samples, though, we actually can take advantage of some normal approximation forms of the tests, whereas in small n cases, we'll need to use tables of values for our calculations. Now, ultimately, this is more of a caveat because in practice, we're not going to be really calculating the Wilcoxon rank sum test by hand. We'll leverage R, SAS, data, or so on. And the one caveat I want to make is that, again, this is strictly speaking, in all cases, this will be true. The null hypothesis is that the mean ranks are the same between groups. However, in our last point here, if we assume the two populations we're sampling from have the same shape, even if they're shifted around, so maybe they have different medians or mean values, then the Wilcoxon rank sum test could be considered a test of the medians or potentially even the means, depending on the distributional shape. However, this is a strong assumption. Many times when people interpret it this way, they actually have not evaluated the shapes and decided definitively that they are the same and maybe just shift it from one location to another. So we'll always be safe using the null hypothesis the mean ranks are equivalent, but in certain circumstances it can be considered a test of medians. So the general procedure for calculating this, if we were to do it by hand, we would pool our two samples of data together and rank the observations from smallest to largest. However, while we do this, we'll still keep track of which sample the observation is from. And if we happen to come across ties, we'll assign the average rank for them. So for example, if we have two data points that are the same and they're the 10th and 11th rank, instead of assigning one randomly 10 and one 11, we would just assign both 10.5. And the same holds for even further ranges. If we have 10th, 11th, and 12th, all three would be assigned a rank of 11. Once we've ranked these observations and calculated their corresponding ordering, we'll then calculate our test statistic, which we'll define on the following slides, and the corresponding p-value. If we have just 10 or more samples per each group, we can use a normal approximation, so introducing some asymptotic properties here. But otherwise, if we have values in either group less than that, we can calculate an exact p-value based on exact distributions. So first, the asymptotic version of the test. I'm not going to spend a ton of time deriving this. I mostly want to include it for your information, as well as the following slides, exact version of the test and the example calculating it before we see how we do it in R. But I think it is helpful to note there is a formula we could reference or go back to and some statistical theoretical properties to leverage. So for example, if we let R1 be the sum of the ranks in one of our samples, and in most cases it's an arbitrary choice, although as we'll see for the exact version, some tables may require you to choose the smaller of the two sums. We can take that then perspective and calculate the expected value of that statistic R1 of our ranks and the variance that someone's derived as well. Again, if there's ties, we have some special calculations we have to do, but in this asymptotic version where we have at least 10 per group, ultimately we see a calculation relationship here to our standard normal distribution via the z-statistic, which we can use to estimate the p-value. In fact, what we can see here almost as a connection is that we have our comparison of what's observed minus the mean, so our observed R1 minus the expected value mean of R1. Because it is using ranks and discrete data, we then apply a continuity correction and then divide it by the variance of our estimator. The exact version of the test is a similar approach. However, because we have small sample sizes and are worried about some of those asymptotic properties, we instead use a table such as table 12 from our Rosner textbook. Here we see that depending on the desired alpha level, you would find the corresponding t-statistics and then take the values and use for our calculations. So let's see an example applied with the Wilcoxon rank sum test in ophthalmology. So we have this case where different genetic types of the disease retinitis pigmentosa are thought to have different rates of progression, where the dominant form of the disease progresses the most slowly, the recessive form of the disease the next most slowly, and a sex-linked form progressing the most quickly of the three. Our hypothesis can be tested that this is true by comparing the visual acuity of people ages 10 to 19 who have different genetic types of retinitis pigmentosa. So suppose that in our sample specifically, we have 25 people with dominant disease and 30 with sex-linked disease, looking at the two extremes of this distribution. The best corrected visual acuities, when they have the appropriate glass or corrections on, in the better eye of these people, are presented on our next slide to analyze. So we may ask ourselves, how can these data be used to test if the distribution of visual acuity is different between the two groups? And obviously, since we're in the Wilcoxon rank sum set of our slides, we can test if the mean ranks are the same or potentially the distributions are the same with the Wilcoxon rank sum test. And so just briefly here, we see that we have our data here on the left-hand side summarizing what we've observed with vision ranging from perfect 20/20 to progressively worse up to 20/80 in our sample. Over here on the right-hand side, we then see various summary statistics we can take advantage of for the by-hand calculations on the following slides. In general, what we seem to see, at least from a first glance, is that it does appear that the sex-linked has a greater distribution or spread of acuity, and the dominant seems to be better and more concentrated towards better vision. So again, this is just an example of a manual calculation. If you want to walk through it, you can pause the video and sort of check it out more. I won't delve too much into it other than to note at the very end, we get a very small p-value suggesting that there is a difference in the mean ranks between those with a dominant or a sex-linked variant for RP. What instead we can do is leverage R to implement this test for us, because quite frankly, ain't nobody got time to derive a bunch of by hand derivations. What we'll take advantage of is this package coin and also epi tools to convert our table into a data frame with a row for each observation. So again, the first thing we do here, we'll define a matrix Y to replicate the results we had on the previous slide for our table. We'll then use the expand table for that matrix Y to transform it automatically into a data frame. And then we can, for example, in the next line of code here with call names, rename it so we have informative titles for each of the columns. two little tweaks we then should note as well, just based on how the data needs to be set up for the coin package's Wilcoxon rank sum function, is that we want our acuity to be a quantitative trait. So again, that I condition of 20, 25, 30, up to 80. But we then need to define our group membership as a factor variable. Otherwise, we'll get an error kicked back. So what we can see is that in this package coin, we can implement this Wilcoxon rank sum test using the Wilcox_test function. And we can implement both an exact and an asymptotic test. So in this case, we wouldn't really need an exact test because we have more than 10 per group, but we can compare p-values in the two approaches. What we note here is that first off in our output, once we run it with our outcome acuity compared to our group of dominant or sex-linked, we see that it tells us it's running that Wilcoxon-Mann-Whitney test, so a slight different naming here than the Wilcoxon rank sum, but equivalent, the same idea. And we see we get, again, a very small p-value, clearly less than 0.05. Likewise, if we just implement the asymptotic test, we get a p-value that is equivalent to what we calculated by hand, just a little more precise to more decimal places, but essentially rounding to 0.00015, which also is less than 0.05. So our conclusion from the Wilcoxon rank sum test, strictly speaking, is that because the p-value is less than 0.05, we reject the null hypothesis. And because we did not evaluate if the distribution appeared the same between the two groups, we're only going to conclude that the mean ranks are not the same between the groups because that p-value is significant. As a different example, just to illustrate why it's not by default a test of the medians, let's look at a very simple case study of aromatherapy. So the primary outcome measure was a 4-level verbal descriptive scale, or VDS, for nausea after an operation. We have two groups, one who received opioids and one who did not, for postoperative pain. The Wilcoxon rank sum test, if we were to incorporate this data and then do all the steps on the previous slide, should come up with a p-value of around 0.001. However, if we look at the summary of our statistics, we first note that they are skewed pretty heavily towards this ordinal category 0 for no postoperative nausea. And also then if we calculate the median score, or 0, 1, 2, and 3, and treat them as numeric values, we see in both cases the no opioid and opioid group both have medians of 0. So in other words, even though the Wilcoxon rank sum test is significant, it is not actually, by default, a test of the medians. Strictly speaking, what we're saying here would be that the mean ranks of our two groups are significantly different between the opioid and no opioid groups. So a few closing notes for the Wilcoxon rank sum test. The first is that it is approximately 95% efficient when compared to a 2-sample t-test if we have normally distributed samples of data. And in fact, it's more efficient if we have deviations from normality with heavy tail distributions, and it's been shown to never be less efficient than 0.864. However, even though people will say this has a reason to consider using nonparametric methods, I do just want to put a thought in your mind that these are not testing the same null hypothesis. A t-test is explicitly comparing the means of two groups for a 2-sample t-test, whereas the Wilcoxon rank sum test is comparing the mean ranks of two groups. Or potentially, if we think the distributions appear similar with just a shift in the location parameter, it could be considered a test of the medians, but regardless, not testing the same null hypothesis. Another point here, number 2, is that our Wilcoxon rank sum test, if we're comparing more than two groups in a pairwise fashion, can lack transitivity. So for example, we can end up with a weird case where x1 is greater than x2, x2 is greater than x3, but also x3 is greater than x1. One remedy to use this that we will discuss later in the semester is the Kruskal-Wallis nonparametric test, which will compare the mean ranks of multiple groups simultaneously to prevent this non-transitive property. Again, the Wilcoxon rank sum Mann-Whitney or Wilcoxon-Mann-Whitney test is widely used in the literature in situations with small samples and or heavily skewed or crototic data. So just be aware as you're reading the literature both what people are claiming their results state and also how they frame what they've actually done. Did they compare the distributions and evaluate their assumptions? But you are sure to see it in many cases, or if you write papers in the future, at some point you're likely to get a reviewer who asks why you did or did not use a nonparametric method. For additional details, if you want to learn a little more, we have 2 papers in our Canvas paper repository by Fagerland and Devine et al. That discuss some additional Wilcoxon rank sum details and assumptions. Okay, so maybe at this point you had heard before there was a test of the medians, and I hopefully have thoroughly discouraged you that that is not the case, at least not wholesale. But you may now be wondering, am I even able to compare medians without making the assumption of the identical shapes of the distributions, or is statistics total trash? Well, if you are truly interested in comparing the medians between samples without assuming the identical shapes of the distributions to use the Wilcoxon rank sum test to do so, we do have some alternatives we can consider. One is there's something known as Mood's median test, and I include a link here to describe more of it, which can also be implemented in the coin package in R. And it's ultimately a special case of Pearson's chi-square test that will test the medians. Something a little more robust and advanced is this idea of quantile regression, which can be implemented via the quantreg package in R, and not only can evaluate the median, but any quantile of interest. You can also, because it is a regression framework, adjust for other covariates. However, this is beyond the scope of our material for this semester, but I do include a link if you want to learn a little more. And finally, we'll see at the end of this lecture, we can use the sign test to test one sample context where we have a proposed null value for the median we explicitly wish to test for. So there are options, just we have to be careful with the ones we're choosing to do and use and how we interpret the corresponding results. So let's briefly introduce the idea of a Wilcoxon signed rank test. This is related to our Wilcoxon rank sum test we just discussed, but it's for quantitative paired data. What it's going to do is incorporate the sign and magnitude of the differences in our paired data, and it can also be useful if the outcome variable describes ordering, but not necessarily some form of physical distance or difference. So for example, if there's an unequal or unknown magnitude between points, such as an ordinal versus a discrete scale. As an example, we may have a Likert scale where we know that 1 shows someone's much improved, down to 5 where they're much worse, but there isn't a concrete difference or distance between 1 to 2, 2 to 3, and so on. The Wilcoxon signed rank test is similar to the Wilcoxon rank sum test, but it's based again on those paired differences here, and again is not a test of the median difference. We're not going to go into tons of details, but we will see an example of an implementation in the next section. But Devine et al. Also have a paper from 2013, which you can look at, that's a review of analysis and sample size calculation considerations for Wilcoxon tests more broadly. So with that, let's get into our last nonparametric test for this lecture set, the sign test. The sign test will be most useful if we have quantitative paired data, x, y, if it can be expressed in a way that is x greater than y, x equals y, or x less than y. If we happen to have numeric values or ranks that are of interest in analyzing, we do already have methods we've discussed that would result in greater power. So for example, t-test to compare means, or the Wilcoxon signed rank test previously for paired quantitative data. For the sign test, we will define our test statistic as p being equal to the probability that x is greater than y in our pairs. And we're then going to test the null hypothesis that p is equal to 0.5, or put into English that for any random pair of measurements, x and y, it is equally likely for either one to be larger than the other. Various special functions exist in R to do this, but we can simply use binom.test with a default p equals 0.5 for our null hypothesis value to implement the sign test for paired data. We can also, as I mentioned previously, use the sign test for a one sample evaluation of the median, where we'll compare the one sample observed median to some null value. To do this, we can either use the sign.test function from the BSDA package or the sign.test function from desk tools. To see how this applies, let's look at two examples with the sign test. One comparing two observations or groups, and one then comparing a one sample. Here we're going to look at deer hind leg length, where a study was completed to compare the deer hind and deer foreleg length in centimeters. We see we've collected information on 10 different deer, and then we've summarized if the hind leg is greater than the foreleg. So we see there's 8 cases where it's true and 2 cases where it's not. Again, we can implement this in R instead of doing these calculations by hand, and we'll see a couple examples of our calculations and conclusions in different ways. The first thing we'll note is that we are going to see here, after we create our data into a data frame called deer.data, the implementation of the explicit sign test from the BSDA package. Once we run it, we get this chunk of output here, where we can really home in on our p-value of 0.1094. Now, because that is greater than 0.05, we fail to reject h0, that the probability of either pair being greater than one another is equal to 0.5, and therefore we cannot conclude that the hind length and foreleg length in our sample of 10 deer are different. Now, this was the implementation with the sign test, but on the next slide we'll see how it would be analyzed if we use the binomial test. So again, recall we noted on the first slide about the sign test that we could calculate the number of times we see x greater than y, and then compare that to the probability of it being 0.5. We can do this in R with the default binom.test function in base R that we can run right when we start R. And what we see here is that we get, again focusing on our p-value, the exact same conclusion. So we see here that the p-value for our exact binomial test matches the p-value for the sign test on the previous slide exactly, and the two methods are equivalent. We can also then just briefly illustrate that difference with respect to potential power, depending on what we wish to compare, with the Wilcoxon signed rank test for quantitative paired data, or the paired t-test if we want to treat them as normally distributed. Again, we can note that these are both more powerful than our binomial test or the sign test on the previous two slides. For the Wilcoxon signed ranked test, we see here that it's from the coin package has a p-value less than 0.05, and even further, a p-value from our two sample, or the paired t-test for our two samples, is 0.0077. So in both cases here, if we were willing to make the assumptions about what we're testing, and the magnitude might matter, well then the Wilcoxon signed rank test would suggest that there is a significant difference in the mean ranks between our tests when we consider that paired nature of the hind and foreleg, and likewise if we're willing to assume the data is approximately normally distributed, we would conclude that there is a significant mean difference between the matched hind and foreleg lengths. As a final change of gears, let's just see a case of the one sample sign test to compare the median to some presupposed null value. We'll look at this case of a length of stay for patients undergoing a procedure based on then what we observe at a hospital to be a range from 4 up to 18 days. The hospital in question wishes to compare this to the national reported median of 14 days for length of stay for patients who have this procedure. In this case, we'll use the one sample sign test to evaluate this hypothesis implemented in R on the following slide. And here we see this implemented with the BSDA's package sign.test function. Again, we will read in our vector of values there for length of stay, and then we'll simply, using sign.test, say x equals our vector, and then m equals that null value we wish to compare to of 14. When we implement this in our model, we get a couple things we can take note of in the output. One, of course, is that p-value we wish to interpret, and again here we see it's greater than 0.05. Another thing that's nice to note, though, however, is that we also get the estimate of the median from our sample in the output, so we don't have to calculate it in a separate step. And we also then get a confidence interval for this median value as well. What we can conclude then from this test is that for our one sample sign test for medians, we fail to reject H0 because a p-value of 0.2891 is greater than 0.05, so we don't reject the null hypothesis that the median is equal to 14 days. Therefore, we cannot conclude that our sample's median of 10.25 days is significantly different than the national median of 14 days. So just a brief conclusion about our nonparametric methods that we've discussed this week. One, nonparametric methods are a useful tool when we are concerned about distributional assumptions. However, they are frequently misused and misinterpreted, especially as a test of medians without evaluating the appropriate assumptions for things like the Wilcoxon ring sum test. So caution should be taken when using them and consuming them in the literature. Another important thing to note is that many parametric methods are fairly robust to departures from their assumptions about normality or other asymptotic properties, so it may be okay to evaluate in your given context the use still of a two-sample t-test versus something like the Wilcoxon ring sum test or other alternative tests. So as we ponder these thoughts, we'll ride off into the sunset with Frank Wilcoxon on his motorcycle thinking about these rank-based comparisons we can do non-parametrically.